I hope not. All right, guys, let's go ahead and get started with the actual content of this course now that we've done an overview. As I said, here we're going to talk about the basics of proper design. We're going to try and start from the beginning. I'm going to be doing some hand waving. Physics, how to use physics to create a transistor, how to use transistors to create gates. And that's where we're going to start, because eventually we're going to have gates to create circuits, circuits to implement a processor, which can then run your instructions. I took these from Dr. Gary Tyson. See, I cited it. It's no longer academic dishonesty. Whew. Just helping y'all out, guys. All right, levels of abstraction, different ways to think of it. At the very basic, we think of the quantum level or solid state physics. How do electrons and atoms work? Conductors, next we create conductors and insulators and semiconductors from our quantum physics. How do we dope silicon to make diodes and transistors from our insulators, conductors, and semiconductors? How do we build gates, logic, and truth tables from our diodes and transistors? How do we make our computational logic, aka muxers and decoders? You don't understand what these words are, that's fine. I'm just trying to help you understand there's tons of layers. Once you have the mux, you create the muxes from the gates, put a clock on top of it.
I know that one.
Got the clock? All right. Latches in memory. You use a clock and the muxers, decoders, and a bunch of other stuff in order to make that work. State machines, well, that's a big one. You have to use latches in memory in order to create a state machine. Processor control, you gotta have state machines inside the processor in order to make machine instructions. And then finally, computer architecture. We define what those instructions are. Tons of layers. We'll be going through them real quick. So we'll start with materials. We have a conductor and an insulator. Conductor permits the electronic flow easily. All right, a lot of high school teachers try and explain electricity, and sometimes they explain it poorly. Always think of electricity as a flow. It's not like you're shipping one piece of data. You are flowing it. Something is flowing around in a circuit. So a conductor will allow it to easily flow. It has a low resistance to electricity, to current flow. This is normally thought of as a lattice of atoms with free electrons, because if it has some free electrons floating around and you push an electron on it, it can easily push all the electrons and push the one at the other end off. And that's the flow of electricity. That's what's going. Pew! Insulator. Something that's a very poor conductor of electricity, aka high resistance. Lattice of atoms with strongly held electrons. You try and push electrons in it, it doesn't give because it's holding strong to what it currently has. It's not willing to give it up. It's not sharing. Semiconductor, material that can act like a conductor or an insulator depending on certain conditions. So variable resistance to flow depending on what you do to it. All right. Any questions on these three? Good.
The easy ones.
So we just do, all a processor is we put a bunch of these things on a silicon chip, hook it up with wires, and we're done. That's it. Nice. That's all a chip is. It's all right. We choose silicon. Anyone know why we choose silicon?
I assume it's going to be on the next slide.
It's cheap.
It's cheap. That's a good answer. So silicon, if you look at the atom, it has an outer shell called baryons electrons, which means that it has electrons that can easily move from one atom to another. So there's an outer shell, because an atom may have a bunch of inner shells that it holds tightly. Silicon, while what's holding onto its electrons, the outer shell is allowed to basically share with other nearby atoms. So, for example, this electron and that electron may swap, and that's fine. It makes it easy for those 4 electrons to swap. Notice that it's a 14, so while it has 14 of them, only 4 of them are swapping. All right? We're good so far.
Mm-hmm.
All right. So which one is this? Semiconductor, because it doesn't have free electrons, and it also isn't holding tightly to its electrons, so it's a semiconductor. All right, we can increase the conductivity by adding atoms of phosphorus or arsenic to the silicon lattice. They have more electrons, one more, which is free to wander about. That's called n-type doping, since we add some free negatively charged electrons. So you have all this, you have a free electron here that if you know you had phosphorus over here, he could just bounce all the way over. And that's perfectly fine because these guys share electrons. This guy over here has one, they can just bounce around. Easy to move around. So what is this? If you have an electron that can move around easily, it's a conductor because it's going to allow you to push the electrons or allow you to have an electronic flow through the lattice. All right, this is a little confusing, but important to understand. An interesting alternative is we can improve conductivity by adding atoms of gallium or boron. They have fewer electrons. Now remember, I said an insulator holds strongly to its electrons, but this one is going to have fewer electrons, which creates a hole. A hole can then conduct an electron by stealing it by someone nearby. So it's not holding strong, it's creating a hole. This is called p-type doping because it's kind of like positively charged is where it's coming from. I'm using positive and negative because if anyone remembers the good old Ben Franklin skit where he got the charge backwards and now all our flow diagrams are literally in reverse. So I have to put them in quotes trying to make this clear. All right, so for example, gallium, oh no, we're missing an electron here. But that just means that if you pushed electrons from over here, there's easily a hole for it to jump into and then maybe move on to the next one as well. So this is a type of conductivity. Science! Okay. So we're going to start, how do we make a chip? We get a pure ingot of silicon, there's a good picture of it, and then we carefully add phosphorus, arsenic, gallium, boron, and put some metal wires. All right, we're done. That's all a chip is. No joke. That's all it is. Carefully add in the right spots.
We don't even know.
All right, talk a little bit about wafers. Here's another good picture. Another picture of the packaging, which I don't think I did earlier. Your chip is right here. Notice your packaging, plastic part with your feet, is a lot bigger, and it connects the metal wires or feet up into the chip.
Also helps protect the chip.
Yes. We good with this? Mm-hmm. All right. All right. The first big thing we want to do is a doping silicons to make a junction diode. Diode is going to be the basis of a transistor. So we need to figure out how does a diode work? How can we make a diode? The junction diode, if you remember diodes, they only allow current to flow in one direction. So you can make it go one way, but current will not flow the other way. So it's a conductor one direction and an insulator the other direction. Okay. Did you tell what's going on? No. Okay, let's go look at this. We got, if you have N-type, think of this all as silicon. Remember, your base is silicon. Up here, you will have an N-type, which is free electrons. So this is with your arsenic, the extra electron. Donor atoms, that might be your boron, yeah, with your, that could suck it in, basically. The P-type. The P-type, you have everything similar, but it's on the bottom. Or free holes, sorry, your holes are down here. And then you have your acceptor atoms. Oh, I'm sorry, I got this all backwards. See, it's even hard for me to get this straight. N-type, all silicon. You have your arsenic on top of the free atoms, and what's happening right here is this is where your regular semiconductor is that can easily accept the atoms. Down here is the opposite. You have your free holes, with of course the acceptor atoms being able to either donate or easily push to it. All right. So we join these together with a junction. What do you think is going to happen when you join these two together? You have
Balance out.
free electrons up here. Yeah, it's going to kind of balance out, kind of.
That's right.
First thing that happens is these free electrons are going to try and cross and go into the hole because you have extra ones. It's like pushing it, so to speak. This guy's sucking it, so to speak. Again, waving my hands. And it's going to cause basically an equilibrium where you have some free electrons here, some holes over there, but they can't really get to each other because they're kind of semi-insulated here. All right. So, let's see what happens. Depletion zone is made with the atoms in the completed outer shell. So you got the depletion zone, and you have some extra free atoms here, some holes here. All right. So the question here is what happens with no current, equilibrium occurs, and the depletion zone basically acts as an insulator because nothing is flowing. You don't have any, it's not creating an electric charge or any current. So that's the standard operation. On the other hand, if you connect the n-type to negative, which means that you're going to be having the electrons being pushed this way, it's going to have electrons here, and your depletion zone is going to get smaller until it can get past the low resistance that you have, and then it'll be able to push it down. And then current will flow. So if you push electrons this way, the depletion zone gets smaller until it connects, and then the electricity can flow through. On the other hand, didn't get a picture of that. If you pushed for the holes, the electrons are going to go into the holes, the depletion zone is going to expand because these electrons that are down here are going to go up here, and then it becomes an insulator. All right? Everyone got it?
Sure.
All right, do review this. You'll have a couple questions on your midterm.
So you're pushing, so you push the whole, what are you pushing to, on this one to?
So this one's pushing negative n-type to native. Okay, you're pushing negative.
Both sides, okay.
You're pushing electrons this way. All right. Again, all the process is a bunch of these diodes connect together via metal wires, and you call it a day.
Okay.
All right.
Good to know.
Transistor. How do we create a transistor? What does a transistor do? It is a switch. Basically like a light switch. It either allows current to flow or it doesn't allow current to flow. Notice that it only allows or disallows. It does not produce a current. It only either allows the flow or stops the flow. All right, how do we do this? We're going to have the n-type with the p-type that we talked about earlier with an n-type on the other end. So it's like this, only you're going to have another one of these on this side. Okay? And then the bottom is just going to be a bunch of p-type, aka holes. And then you're going to have a gate on top. Okay? So this is a switch. So here's what's going on. Source, n-type, all this is a p-type silicon, n-type silicon with a gate on top. Without this gate, if you were to try and push over here on the source, what would happen? Or actually, it's not going to show you. If you try and push right here, it's actually going to first go into the p-type and act as an insulator. On the other hand, if you push on the gate, which you apply voltage here, it's going to fill in this part of the p-type, which will then make it basically a neutral charge, aka a semiconductor, and then the electricity can flow through it. These arrows, I know, look like they're backwards. Again, you can all blame Ben Franklin for that. But the point is, you apply voltage to the gate, it fills in these holes up top first, and then if you have current, it can flow through. If you don't fill in these first, when you apply current, it's going to try and fill basically down here and act as an insulator. All right. Everyone good with me or following so far? Okay. And I think that's all we're going to do. Right, because if you just apply, normally it goes into the p-type and acts as an insulator. Good. We're going to stop here. And at least look at your lab.
Nah.
It wouldn't be a
There was
Dr.
catch.
It wouldn't be a Dr. West course if you didn't have a lab, right? On the first day.
As long as there's not